Hello, everyone. I hope that you're all doing okay today on this another rainy day. Welcome back to Comp 2160 Programming Practices. Today, I brought my Game Boy with me, and so this is my modded Game Boy. And I mean, I don't know if you've ever seen a Game Boy Color before, but they don't look like that. Like the accessories that you used to have to buy to get lighted screens on these things was crazy. This is Pokemon Yellow. And so specifically, if we're thinking about Pikachu, if we're thinking about zones here, if I go to continue here, and like a zone here might be, this is impossible to play when looking at the screen like this. A zone here might be we're on the current screen and we destroy it. And as we leave this building, so we leave A's house, that whole zone is going to get destroyed and a new one might be created, kind of like waiting in the background for us. This Game Boy is also modded with like a rechargeable battery in it. I'm really proud of this. I'm really proud of this item. These mods were less involved than I expected them to be, but still, I'm proud of it. I'm just like unreasonably proud of how I've modded my Game Boy. Yeah. Well, there's so many questions right away. Yes. Yeah. So if you go back, it would go through the process of having to like destroy the zone that you're in and create a new zone. Yeah, and then reallocate all those things in it. In terms of the code that's running on this, again, I can't actually say what's happening, but if I were thinking about this in terms of zone-based allocation, it'd be like, as you leave the building, destroy everything that's been allocated for the building, and then just create a new zone and start allocating everything that's outside the building. When you go back in the building, destroy everything that was allocated for outside and just start allocating things for the building side of the building. Yeah. Yeah. No, this screen that I bought is a fully, and it's kind of like you buy the whole thing. It's a laminated screen. So here, I mean, it's going to be better if you just look at it. You can see that the screen is like right up against the glass. And then you can adjust the brightness by tapping the top of the screen here. And the color here for Game Boy Color is you can customize the color on it. Yeah. Yeah. I've seen it. Like my partner has played it and my son has played it, but I don't know. There's when I watch it and like being able to see the whole world around you as you're going makes it seem like just a little bit unnatural to me. And I don't want to gatekeep Zelda, but that's not the way that it should be. Yeah, it feels like an actual open world as opposed to you're looking at a screenful at a time, but I'm so used to it being a screenful at a time that, yes, yeah.
Have you seen Matt Casey's YouTube videos?
I haven't heard of this. Matt KC. Okay, I will look this up right now. This is the best use of our class time. Me looking up YouTube channels. MATTKC. Whose channel is described as nerd. Okay, I'm subscribed. Where was the other question? I'm going to answer that question by saying wait for about 30 seconds and then we'll start talking about it. Yeah.
Did you ever play Ocarina?
I didn't play Ocarina of Time, no, because that was GameCube, right? Was it N64? You know, the game that I played mostly on N64 was GoldenEye and Wave Race, which was like it's like a racing game on Sea-Doos. I don't know. Okay. All right. I suspect that everybody thinks that their generation Zelda is the best Zelda of all time. Yeah. I'll say that they remade Link's Awakening, so that further justifies that it's the best Zelda. But yeah. Okay. Anyway, today we are going to be visualizing this code. So this code is on the course webpage. I'm going to try to keep this code open while I'm doing the visualization, but in that I want the visualization to take the bulk of the screen. I'm probably not going to have like large swaths of this code open at any given time. So if you do want to see this code up at this on your screen the whole time as I'm going through this, please download a copy of this. This is also in yesterday's sample code, so you can find it up on the course webpage under lecture 16 and lecture 17. So the two outcomes that I'm looking at us to be able to do by the end of today are, so this is continuing from yesterday, describe concepts of in-application memory management, such as first fit memory allocation, the runtime stack and the heap and garbage collection. Yesterday, we finished the heap. In terms of like allocation policies in the heap, we're going to leave that right now as just question mark, question mark, question mark. The key things that I want you to be able to describe about the heap are things like where it's physically located in an address space for a process. So we've got code heap stack at the bottom. I want you to be able to describe things like the lifetime of a value that has been put into the heap compared to the lifetime of values that are put on the stack. The stack is kind of ephemeral. So ephemeral means like it's there for a little bit and then it goes away after a while. In terms of the way the runtime stack works, we push something onto the top of the stack, stack frame. Values are allocated within it, and then we pop off of that stack frame. And the lifetime of that value ends as soon as that frame is popped off the stack. In terms of the heap allocated variables kind of have a lifetime that is as long as they are not released for reuse or until the program ends. Once our program ends, the operating system kind of comes in after us and cleans up everything that our process has allocated. So if we write code that doesn't call free for every malloc, our allocated memory will still get released when the operating system comes in and cleans up after the fact. And that's fine for very short-running programs, but things like web servers that are running for a long time, that's going to lead to memory leaks because they're not going to get shut down very often. Today, our goal is to focus on first fit memory allocation, and then specifically in the context of this zone-based allocation and zone-based memory manager. The other thing that I want to get to today is to describe the benefits of modularity. So we're going to take a step back and start thinking about software design again. And I want you to be able to use simple metrics to specify or measure the degree of independence between two things, between two concepts, between two physical pieces of code. And the words that we're going to be using to describe this degree of independence, how related they are to each other or how unrelated they are to each other, is coupling and cohesion. So we'll talk about those two terms, and these are words that we're going to use to measure the relationship between pieces of code. So just quick intro. Memory managers, including malloc. So malloc, the one that we've been using right now is from something called glibc. This is the standard library implementation of the C standard library. Again, on Mac OS, it's the Mac OS implementation of that, the BSD version. But on terms of Aviary and Linux, we're looking at glibc specifically. These memory managers use different kinds of allocation policies when managing the heap specifically. And some of those are best fit, worst fit, first fit, and next fit. In this class, I've highlighted the wrong one. We're going to be looking at first fit. I meant to highlight first fit here, not next fit. We are going to be looking at the first fit allocation policy. The first fit allocation policy is pretty straightforward. It is, if you've got some chunk of memory that you are managing, and then allocation metadata about how that memory has been allocated already, we do a linear search starting at the beginning of the chunk of memory that we're allocating to find the first free space that's big enough to satisfy the request that we're trying to satisfy. So keep this in mind. we've got a chunk of memory, we've allocated something, we've got a big block of something that we are managing. We will have metadata about it that says this is allocated, this is unallocated. And first fit is do a linear search, start at the beginning and work your way toward the end until you either find some place that's big enough and is not allocated, or you get to the end of that chunk of memory and you have not found something that's big enough. So you cannot satisfy that request. Let's take a look at this code using zones.c. I want to step through the code, and then I want to execute the code, and then like draw diagrams that describe what's going on with this code. So I'm going to pop this up on my screen. This code does not call malloc. So this main file that I have for you here does not call malloc. We are going to be using the memory manager that you are going to be implementing. So this code does not call malloc. It just assumes that you are in charge of everything. Your memory manager is in charge of everything. On the stack in the main function, we've got a few different variables. So hello and Kraken are just two pre-allocated strings. These are C strings, so we can use the string.h library. They've got our null terminator. This is that normal stuff that we've seen so far in terms of strings. I've got two variables here that are pointers to char. I'm going to copy the contents of hello and Kraken in just a little bit, and I'm going to dynamically allocate that using the memory manager. I'm going to ask the memory manager to allocate this space for me. I'm also going to dynamically allocate an array of unsigned char. These are going to be numbers. I'm choosing unsigned char here specifically because I want each number to be 1 byte in size. So now I'm making a choice of type because I want to specify how many bytes each thing should be. And here I want each number to be exactly 1 byte. An unsigned char is always going to be 1 byte of memory. So to use this zone on line 15 here, I'm going to initialize the zone. So I'm going to call the constructor function. And internally, this memory manager is going to go through the process of creating all the structures that it needs. It's going to dynamically allocate 2 things on the heap. So inside the memory manager, you're going to call malloc 2 times. One is going to be to allocate a structure, something that's big enough to hold 16 bytes of space. So we're requesting a zone that's 16 bytes big. So you should allocate something that has 16 bytes of space. The other thing that you're allocating is whatever your internal structure for a zone is. So we're getting a pointer to a zone. You have to create the structure yourself, and then you will dynamically allocate that structure and return it. On line 19 here, we're calling the first z_alloc. So this is the first time we're asking for space within the memory that's managed by the zone object. We're asking here for strlen hello. Hello is hello, exclamation point, and then the null byte. So we've got eight total bytes of space that we're trying to allocate. Z_alloc can return null if it's not able to satisfy a request. So if there isn't enough free space, this only has 16 bytes. If there isn't enough free space left, when I call z_alloc, it's going to return null. So I have to check to see that it doesn't return null. If it does not return null, what it's returned to me is a pointer to the beginning of 8 bytes of space. So kind of the same way that malloc does. Yeah? A post condition for z_alloc for me would be that I am either returning a non-null pointer or I am returning a null pointer and there's not enough free space to allocate that many bytes that's been passed to me. That's just something that you'll keep track of internally. Yeah. Again, I'm gonna draw this out. I just want to step through the code first. So internally, you're going to be keeping track of a bunch of different metadata that's attached to this. Yeah. So zalloc is returning an address to us. It's returning a pointer. So in copy 1 now, what we've got is an address that has 8 bytes of free space. So I'm just going to use strncopy. This is just that regular string library copy function. And I'm going to copy from hello strlen bytes, and strncopy adds the null byte at the end, and I'm going to copy it to copy 1. My printf here prints out what the original string is, what its address is, so %p, and then we're printing out what the copy is and what the copy's address is. I'm trying to show that they have the same values, but they point at different addresses in memory. They're not physically the same thing. On the next line here on 28, we're doing something similar. I'm trying to allocate 5 bytes of space, so 5 times size of unsigned char. Again, unsigned char is always going to be 1 byte. Trying to allocate that much space. This has 16 bytes in the zone. So after allocating 8 bytes, there's still 8 bytes free. So I can call this, and I should not get null back. Here I'm just treating numbers as an array. So I'm doing subscripts, and then I'm putting numbers into this. The address that we get back from zalloc is the beginning of someplace in its managed memory where there's 5 bytes of space. So I can start working with the 5 bytes of space. On line 39 here, we are releasing the first string that we allocated. So this is saying that first thing that we had copied, I'm going to release it. Internally, my memory manager is now free to reuse those initial 8 bytes that it allocated for my first call to zalloc. On line 41, I'm going to allocate just 7 bytes. I've chosen this value specifically so that we can take a look at what first fit is going to do here. First fit is going to be forced to happen in this situation right here. I'm trying to allocate 7 bytes. I do the same thing as I did with copy 1. And then at the end here, what I'm doing is I am not releasing copy 2, and I'm not releasing numbers. So I've released only copy 1. When I do destroy zone Z, my memory manager should go through and release everything that's been allocated internally for it. So I, the caller, don't have to care as long as I destroy the zone after I'm finished with it. If I run this with Valgrind, I shouldn't get leaks. I shouldn't get a report of any kind of leaks because I've called destroy zone at the end, even though I haven't called Z free every time I called zalloc in this code. So I hope that this looks pretty normal in terms of like our experience now with malloc. If I replace zalloc with malloc, this should look like code that you've already written before, except I'm missing some calls to free. Any questions about this so far? Good. OK. So I'm going to pop this up to the top here. I'm going to make this just a little bit smaller. And I'm going to go to the top of my main function. And I'm going to make this just a little bit smaller so that we're at the bottom. And I want to divide this into 2 different regions here. So I'm going to draw a gray line to separate these things. On the right side of this is going to be my public main area. On the right side is everything that's in the main function, everything that the main function knows about. On the left side here is going to be my private memory manager stuff. So this is everything that my memory manager has internally, everything that's being kept track of internally. In the public main area, I'm not going to keep track of things like hello and Kraken, because these are just things that are in the public main area and my memory manager doesn't need to know anything about, those things. The things that I do want to keep track of are the pointers that I'm going to ultimately get addresses from zalloc. So in my public main area, I'm going to have copy 1. This is a pointer. I'm going to have copy 2. And I'm going to have numbers. So these are the 3 addresses that the 3 pointers that I want to store addresses in. On line 15 is where we're beginning to make the zone structure. When I initialize my zone internally, I'm going to have to create two things. The first thing that I want to create is the zone structure itself. I'm going to describe the zone structure, but your zone structure is probably going to look different. You're probably going to have more properties in it than I'm describing right here. It's kind of up to you to decide what you want to have, but minimally, this is what a zone structure would have. My zone structure internally is going to have a linked list of blocks. I'm using the word blocks here to say when I call zalloc, I'm going to allocate a block within the memory that my zone manager is managing. So this is a linked list. I'm going to allocate a size. This is just an integer. This is a z size t type. And in this case, I'm going to populate this with the number that's been passed to me. So I'm managing 16 bytes of space in this zone. And the other thing that I'm going to allocate is the actual data that I am managing. The data that I am managing is I'm going to call malloc and ask for 16 bytes of space. And what malloc is going to return to me is an array. It's going to return to me an address. I'm going to treat it as though it's an array. So I'm going to draw an array here. And I'm just separating this into 2 pieces so that it's bigger visually, but you can assume that this is connected directly to this. You can just assume that these things are connected to each other. So this is one long array. I'm just separating it into 2 pieces so it's easier for us to see on the screen. So this is going to be 8 bytes. This is going to be 8 bytes. This is element 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So we've got 16 bytes of space that we've allocated. So my first malloc is for this stuff here. My second malloc is for this thing that I've got here. The type that you choose for your data variable, I'm going to recommend that you choose unsigned char. Unsigned chars are 1 byte in size. They are always 1 byte in size. Each element will be 1 byte in size, and that's ultimately what we're trying to do here. So after line 15 has finished, this is what the structure of our thing looks like. Our blocks element right now, this is my linked list. This points at null. There is nothing that's been allocated yet. I am managing 16 bytes of space, and I have 16 bytes of space that I can manage. It's a linked list, yeah. You're going to create a linked list. You're going to create a node structure separately, yeah. And I'm going to describe what's in the nodes when we do our first allocation. But when we first create the zone, there's nothing that's been allocated, so there's no nodes in our list. So at this point, we have no nodes in our list, so we have 16 bytes of free space. I can keep track of that as a separate variable. I can have a variable that says free space is equal to 16, but I can also say I've got 16 total bytes and my list is empty, so I have 16 free bytes. I haven't allocated anything yet. Size is going to be Z size T. That's the value type that you're passing to this function. So if you look at the header for make zone, that's the type that you're accepting. So you should use that type internally. Okay, does it help clarify? Okay, yeah.
Is the size the amount of cells in the array, or is it the amount of nodes in the linked list? We have a linked list, but like all different cells in the array.
The size represents the number of cells in this array. So, or number of elements in the array. So I'm going to have 16 elements worth of space to manage. The list itself manages and keeps track of what has been allocated and what has not been allocated yet. So you might have 0 nodes in the list with 16 size, like we're in the state right now, and that means that nobody has asked for us to allocate anything yet. We just have a zone that has 16 bytes of space.
And the array is just in the zone structure, not like each node.
No. So each node has, we'll get to it in just a second, but each node has very little attached to it. Yeah. Yeah. Z size T is, so I'm going to just go back to here for a second. Z size T is this on line 6. It's just a type def of unsigned short. So it's redefining what unsigned short is and giving it a new name. It's just a number. It's nothing out of the ordinary. It's not a bigger structure. Okay. So after line 15 is done, this is the state that we're in. Copy 1, copy 2, numbers in the public main area still point to null. We have no nodes in the list of blocks that we've allocated. We have an array that's been allocated for us dynamically that is the same size as what we have kept in this size property. I'm going to scroll down just a little bit. On line 19 is where we're doing our very first allocation. So this is the first time we're calling zalloc, and we're asking for the zone that we just created, and we're asking for 8 total bytes of space. So inside my zone structure now, I have to begin to do a first fit allocation policy. This is like the easy base case. Nothing has been allocated yet. So if the size that's been requested, 8 bytes, is smaller than the size that I have, then I can just insert a new node to the head of my list because there's enough free space at the beginning of this buffer that I'm keeping track of. So the way that I'm going to do that is I'm going to erase null here. And I'm going to insert a new node. My node structure is going to keep track of how much space has been allocated for that specific node, for that allocation. So on line 619, on line 19 here, the size that we're trying to allocate is 8 bytes. So our size is 8 bytes. This is the very first base case. So the buffer that I've got here, data, the array, this dynamically allocated thing, everything in here has not been allocated yet. And first fit is find the first free unallocated space. The first free unallocated 8 bytes starts right here at element 0 in this list. So I'm going to say that I've also got a block. My block type is a pointer into the buffer. The pointer into the buffer here is going to be pointing at the very start of this buffer here. It's at the beginning. When I call zalloc, you'll read this in the description of this function, but when I call zalloc, it should zero the contents of memory that have been allocated. So to start, it's going to write 0, 0, 0, 0, 0, 0, 0, 0 into all 8 bytes of this block. My node structure has a next. The next in this list is null. I've inserted into the head of the list. I have allocated one thing. I've allocated 8 bytes. The 8 bytes start at the beginning of data. zalloc is going to return to the public main area to get stuffed into copy 1 the address that was allocated for that block. So copy 1 is going to point at the very beginning of this data structure. Copy 1 and my main code don't know anything about the zone, but I can give addresses out that are in the zone. Yeah. This is just the name of a variable here. And so what I'm trying to say is that this is a pointer to the block that has been allocated that is what this node represents. It will have a pointer to somewhere in the data buffer. Yeah. Yeah. The linked list is metadata. It's data about the actual data that they're storing. So it's not the information itself, it's just information that describes what's in there right now. So in terms of this structure right now, we've allocated one thing. There's been one call to zalloc, and we have satisfied that one call to zalloc by allocating that one block of 8 bytes. This okay? Okay, okay. On line 23, we're passing the address that was returned to us to strncopy. strncopy does string copy. It copies n bytes from the source string and it copies it to the target. So what this is copying for us right now is hello, exclamation point, exclamation point. We're passing an address to the beginning of this buffer. So it's going to go through and it's going to write out into this buffer HELLO, exclamation point, exclamation point. I'm going to rewrite that, but just a little bit bigger of a pencil. So it's writing it out as HELLO exclamation point, null byte. So we're replacing the contents. We are not replacing the contents. We're passing addresses to strncopy, and strncopy is writing at the addresses that we've asked it to. When I go to this next line here, line 28, I'm calling zalloc one more time. Now we're going to do first fit again. This is no longer the easy base case where we have nothing in our list and nothing has been allocated yet. Now we have to find the first free space that's big enough to satisfy this request. We're going to start by scanning the list of blocks that we have allocated. I'm going to start here. And what I'm going to do is I'm going to look and see where is this block pointer pointing at in my zone. I can see that this block pointer is pointing at the start of what data is. So right now in this state, the pointer that block has and the pointer that data has are equal to each other. They are the same value. They're the same address. That tells me that there is no free space at the beginning of this block. So I have to go to the next node in my list. The next node in my list is null. I can see that this block allocated the first 8 bytes. And so there's 8 bytes allocated from the beginning. That means that with the size of 16, we still have these 8 bytes here that have been unallocated. So the first free space for us to allocate that, our first fit policy here is we can put it at the end of the list. We can put it after the allocation that's just been made. So I'm going to insert a new node to this list. The new node to the list that I'm allocating is going to have a size of 5. I'm allocating 5 bytes this time. It's going to have a block pointer. And the block pointer that it has is going to point at this address right here. We're going to return that address to main to copy 2. And so copy 2 will also point at this address. And then just before returning, we're going to zero out 1, 2, 3, 4, 5 total bytes. If numbers is not equal to null, then I'm just going to start writing into it. So my main code, not strncopy, but my main code is just going to start writing into that address. Numbers at 0 is the same as whatever the numbers pointer is plus 0 bytes. So I'm going to start writing in at the start of this buffer that's been returned to me, 42. Numbers at 1 is the numbers address plus 1 bytes. And in that spot, I'm going to write 42. Numbers at 2 is the numbers address plus 2 bytes. And I'm going to write into that 42 and 42 and 42. So for each of these numbers at whatever, I'm using the address that's in numbers plus this number in the square brackets. Internally in C, our arrays are just addresses that we're adding to each time. So copy 1 and copy 2. Well, I'm sorry, it's not copy 2 that we're looking at right now. It's numbers. It's my mistake. Please forgive me. This is numbers that has this address. So numbers has that address. Copy 1 has an address. numbers has an address. The first block that has been allocated in my zone-based memory manager is this one that has size 8. The second block that's been allocated is this one that has size 5. And we've got addresses and pointers into each of those. Our public main area, all it knows about is just the addresses that have been given back to us. That's all we know about here. I'm going to keep going down here. On line 39 is the first place where we're calling Z-free. Z-free is going to release the resources that have been acquired for this address, copy 1. To release the resources, I need to go through and find the node in the list that has that address and then remove that node from the list. My zone is always going to manage 16 total bytes. This size of this thing here never changes. It's always going to be 16 bytes. When I free this, what I'm saying is I want to release the resources that were acquired at the address that this value has. That starts right here. So I'm going to start scanning my list. The first node that I have in my list, the head, is coincidentally the one that points here. So Z-free is going to release that resource. Releasing that resource here is deleting that node. So I'm going to erase that node, and now the head of my list is just directly going to be this allocation that's been made here. So I now have just one node in my list. I don't have to erase everything that's in my buffer at this point. When I do zalloc again later, I'm going to zero everything out. But for right now, all I have to do is erase or delete the node from the list. Copy 1, for the record, still has the address that we're pointing to at the beginning of the buffer. But in the same way that we can't or shouldn't use an address after we pass it to free, we can't or shouldn't use the address that we've just passed to Z-free. Still points to the same spot, but we shouldn't use it anymore. On line 41, we're doing one more allocation, and this is another one of those kind of tricky cases of first fit. First fit here says, I want to allocate 7 total bytes. So I'm going to need to look at the list of allocations that I've got. I'm going to start and I'm going to say there's something in this list. I don't immediately point to null, so I cannot just blindly insert to the front because there have been allocations that have been made. My first step here is look at the first allocation that's been made. The first allocation that's been made has an address that is greater than the address that data has. So data's address starts here. This address is way over here. This is 8 more than what we had before. The difference between block here and data is going to be 8. It's going to be 8 total bytes. That means that there are 8 free bytes before the first node's allocated block. There are 8 total bytes there, and first fit says find the first space that's big enough to satisfy the request that's being made, and the request that's being made here is, I want 7 bytes, please. And so, yes?
We call Z-free on 39. Does copy 1 still point to the start of data at that point, or should it be pointing to null?
Copy 1 still has that address in it, yes. But again, free, when I call free with a pointer, it doesn't change the value of the pointer. All I'm saying to glibc and malloc is you can reuse this again.
So it's up to the user basically to know that copy 1 shouldn't point to anything.
Yeah, I cannot stop you. You can't stop me from overwriting that stuff anymore. Once you give me an address to it, I can just use the address if I want to. But you are not guaranteeing to me that you're not going to use it for anything either. You might be giving it out to someone else, and someone else might write into that same area. So, and we've talked about this before. You were asking about returning null and assigning null to something after you do free. If you really, really want to show someone you shouldn't use this again, you could here say copy 1 is equal to null. And just very explicitly say, I'm not going to use that address anymore after I freed it. That was you, right? Yeah, okay. So if I did that, it would erase this pointer that we've got right here, but I don't want to erase that. I just kind of want to leave it because this is how I've been doing malloc and free before. Yeah, okay. Yes, please.
So in that assignment, it says if whatever side is supposed to be a zone the size equals to
Yes.
So then if we get it
Round up to the next multiple of 8. So don't round down, round up. Always round up. So if you get 7 for your zone size, it's an 8-byte zone. If you get 17 for your zone size, it's a 24-byte zone. Yeah. Okay, so we're going to do first fit here. First fit for 7 bytes. We're going to start scanning our list. There's something in our list, so we have to look at what this points at. It's pointing to an address that is greater than what our data buffer starts at. And the difference, and I'm talking about like difference in sum here. The difference between these two addresses is 8 bytes. It's big enough to fit the thing that we're passing in. If I subtract from block data, I'm going to get 8. I'm going to get 8 bytes of space. Yeah. I don't actually care in this case if there's nodes after that. Because I'm doing first fit, I can say there's enough space here, so I'm just going to stick a node in. Yeah. I'm going to be inserting in place. So when I do insertions here, just in terms of making sure that first fit is easy to implement, I'm going to insert in place. So inserting, I'm going to do the insertion right now, and I'm going to insert it before that one. I want to make sure that all of the addresses in block in my list are sequential. Yeah. So my insertion here is going to be that I'm going to erase this pointer, and I'm going to add a new node in my list. So we previously deleted a node. I'm going to add a new node in my list. At the beginning, I'm going to insert it. The size here is 7. The block that this one is going to point at is also going to be the same as what that first one was. This is just a coincidence. So the first node is coincidentally going to point at the first address in my data for my zone. As I was just saying here, when I'm doing this, I'm trying to make sure that the contract is that these block addresses are sequential. The next one is always bigger than the next one because it's going to make it easier for me to say how much space is in between these things. So once I do that allocation, I'm going to zero out 7 bytes for this new allocation. And so I'm going to do that by taking a gray pencil that's really big, and I'm going to fill these in. And I'm going to write in here that each of these entries are 0. So 0, 0, 0, 0, 0, 0, 0. I'm only allocating 7 bytes. So I'm not going to erase this null byte. It is coincidentally also 0. It's coincidentally also 0, but I'm not going to overwrite that null byte from the original 8-byte allocation. This one has only asked for 7 bytes, so I don't need to overwrite the 8th byte that was previously there. What I'm going to return to my main function now is a pointer, and we're going to put that pointer into copy2, and it's going to point at the beginning of the buffer that I have allocated here. Our main function is passing that address to strncopy again. This time we are copying the string that's Kraken. So I'm going to write that in. We're going to overwrite K R A C K E N. And then it's going to write past the end of this. It's going to write this null byte in. That looks terrible. That looks really awful. I'm going to do that same thing again. I'm going to use a gray pen, and I'm just going to erase everything. And then strncopy is going to blindly insert this null byte, because we just told it that it's OK to do that. Our memory manager, just like C itself, cannot enforce null, like array index out of bounds exception. We cannot do that. This is a contract of the language. You have access to the bytes. You can write to the bytes if you want to. You cannot enforce array index out of bounds exception. When I go through to the next block here, this zdump function is going to print out some statistics about my zone. What I want to print out is, where does it start? Where does the address of this thing start? How many total bytes are there in my zone? And how much free space is there in my zone? I can compute how much free space is in my zone by going through this and saying, it's this number minus this minus this. Scan the list and reduce it by however many allocated bytes there are. And that tells me how many total free bytes there are in this thing. When I'm printing this out here, I don't care what's inside of this. I don't actually care what's in this. I just want to see what the metadata is about everything that's been allocated. On the very last line here, when we destroy our zone, we're going to go through and we're going to pass to free this data block that we previously allocated with malloc. So this again is on the heap. We're going to free all of the nodes that we've allocated in our list, and then we're going to free the entire zone itself because we have also allocated that. Yes?
There's no C.
You're right. So I'm bad at counting and spelling is what the answer is here. So here, my point still stands though. You cannot enforce an array index out of bounds exception. You can't enforce that. Yeah.
Immediately allocate like just 1 byte after writing Kraken. Would it put it at position 7 or 13?
If you allocate 1 byte, our first fit policy is going to say, let's scan the list. This one points at the beginning of my buffer, so I can't put it before this. It's of size 7, so the next address that could be free is this one. I'm going to look at the next node in the list, and I'm going to see that this one minus the address of this is 1 byte, which is enough to satisfy a request of 1 byte, so I would put it here. Yeah. Yeah.
So like when you're allocating, basically you're thinking about like checking if there's any other, like already got a block that allocates that point, and then seeing if that point plus the size
Yeah, so you're going to have to use the two nodes that are next to each other to compute how much space is between them, basically. And if there's enough free space between them, then insert a node between them. If there's not enough free space between them, then move to the next pair of nodes until you get to the end. And there might be lots of free space at the end, or there might be none left at the end. But once you get to that end case, it's like, how much space is there after this? So if I do like the address of the last block plus its size, is that less than the length of the overall list? Yeah, yep. So if we're allocating just 1 byte, we're allocating just 1 byte. If we have a string that has 1 character in it, that's 2 bytes because of the 1 character and the null byte. But if we're allocating, if I just want to put a single number into that 1 byte of space, so not specifically a string, then that 1 byte would fit. If you ask for 1 byte and then you did strncopy with a 1 character string, then you're going to put your character here, and then the null byte is going to overwrite this. That's the case that you're thinking about. But that's 2 bytes. That's not 1 byte, that's 2 bytes. Yeah. Yeah, so 9 bytes here, that's a good question. If we try to allocate something that's more than the available free space, so if we just had just this 5 byte allocation here, if we had just that one, there's 16 total bytes, only 5 of them have been allocated, and I want to allocate 9 bytes. I'm going to quickly say, OK, there's enough free space to maybe satisfy this request. So I'm going to start scanning the list. If I try to allocate 30 bytes, you can immediately say no. Just like quick check, is there enough space in this zone? No, there's not enough space. Quick check, yes, maybe there is enough space in this zone. Now I need to go through the list structure that I've got and try to find a space that is big enough for that request. If it's just this node, then what I'm going to find is that between the start of data and the start of this block pointer that we've got here, there's only 8 bytes, so that's not enough to fit 9. After the end of this one, there's only 3 bytes. Then that's not enough to fit 9. So I would return null at that point to say, no, I can't allocate that for you. You don't have to move everything around. Yeah. In some other strategies, we might do that. So like in a garbage collection strategy, we might go through the process of saying, OK, I'm going to shift everything to the top and then see if there's still enough space left over. This is called this idea here that we've got where there's 2 blocks of free space that fit but not contiguous. This is called fragmentation. You might have heard of this in terms of hard drives before. Maybe. It's not something you really have to do anymore. Again, when I was a kid, computers you had to defragment them occasionally because your hard drive would be fragmented. And this is what fragmentation is. There's a bunch of free space, but it's all over the place. Defragmenting is squishing everything to the top, so there's one big free space. We're not doing that in this assignment.
If we started using this for a while and ended up with a bunch of allocations, like in a strength pattern, like only even numbers or only odd numbers, does that mean like the only byte size that we can basically support at that point is just 1 byte?
Yeah. Yeah. So if you have a pattern that looks like, I'm going to allocate 1 byte, 1 byte, 1 byte. So to get into this state in the first place, you'd have to do 16 1-byte allocations. So 16 times I'd have to do this. And then I would have to go through and free all the odd or even numbers to get into that state of, I want to have exactly 1 byte between everything. You can't get into that state with first fit just by doing 1 byte and then 1 byte, because first fit will always push it as close as possible to the beginning of the thing where there's free space for it. That would be a great test case. There's enough free space here, but it's not contiguous, so I can't satisfy anything more than a single byte. Yeah. Okay. Tell me about your confusion. Yeah. Within so in the blocks list, this is a list of nodes. In the node, there's a pointer, but it's just a pointer. It doesn't contain anything except for an address. It's just an address. The address is kind of coincidentally pointing at or inside the data buffer. It's addresses that are inside that range, but it doesn't contain anything. It just points to the address of data. It points to the address of data +5. It points to the address of data +8. It points to the address of data +0. It points to an address that happens to be inside of the data buffer, but it doesn't contain the data buffer. For the numbers example that we've got here, there's no null byte because it's just an array of numbers. Null byte is a special sentinel for strings in C. Yeah. Okay. Okay. All right. As like with the last assignment, I'm going to make sure there's time for questions. I'm going to make sure there's time for questions on Monday. So on Monday is the day I'm going to give you time to ask questions in class about the assignment. But with this description of the memory manager and with the idea of using void pointers, you should at this point have enough to be able to do this assignment. The stuff that we're going to be talking about for the rest of this week is related to the course, of course, but it's not going to be related to the assignment. Any last questions? Up until operating systems, this is going to be the coolest assignment that you're going to do, and it's going to feel really proud when you're done. It's going to feel great when you get something working for this. Even if it's just like the basic stuff, it's going to feel so cool when you can get this stuff done because you're starting to think about, like, this is what my machine is actually doing. This is what malloc is doing internally, and I think that's really amazing. To jump ahead into operating systems, because God damn, I love operating systems. When I do that course, my last assignment is to implement file system stuff. So like you actually, you got thumb drives that you can plug into your PC. On most machines, it uses a file system that's called exfat. And the assignment that I give at the last part of that assignment is for you to implement reading exfat. So you can plug a USB drive into your computer and then read it with code that you wrote. Not just like opening it in File Explorer and looking at the files, but actually seeing the contents of the files. And I think that's amazing. And exfat, for the record, is nothing more complicated than linked lists. It's nothing more complicated than linked lists. It's all numbers, but it's nothing more complicated than linked lists. And then reading bits and bytes, which is kind of a pain, but is what it is. Okay, so I'm gonna leave this. I will publish this diagram for you on the course webpage under today's lecture notes. But I'm going to move on to another topic now, unless we've got any more questions about this diagram. I'll leave this up here for just 5 more seconds. OK, awesome. OK. So I've got, I think, just enough time to talk about this today, which is kind of where I'm hoping to be. I got to this point last week, and I said, I don't want you to do this, so I'm going to skip it last week. I'm just going to skip it last week. And this week, I'm not going to skip it. In Java, we were able to do something that looks like this. We could have 2 completely separate classes. We could declare something as a public static variable, give it a value, and then be able to read it and assign to it from other completely separate classes. You probably didn't do this very often, which is good. That's good that you didn't do this. I'm assuming you didn't do this very often. Okay, I'm assuming you didn't do this very often. The one place where you might have done this is like, I have a constants class and it's got all my constants in it, and you're doing public static final whatever. That's an okay use of this. We can do this in Java. We can also do this in C. If I start with just this structure, where I don't have classes anymore, I have files. I have a file scope variable in file1.c that I want to call thing counter. And in this other file, in some other function somewhere, I want to be able to change the value of the thing that's inside this file. How do I do that in C? There's a special keyword in C that's called extern. Extern is a way for you to say, I would like to declare a variable that's at the file scope, and I want to be able to use it in other files. Static says, I only want to be able to use it in this file. Extern says, I want everyone to be able to see it, and I want to explicitly give access to it. The first thing that we do is we declare and we define a variable in the first file that we are trying to work with. In the second file, we declare it as a file scope variable. We don't define a value for it, so we're not assigning anything to it. And we use this extern modifier. Let's try this out. I'm going to pop open my terminal here. I'm going to close using zones, and I'm going to open up extern. I'm going to call it file1. I'm going to be consistent with my naming convention here. In this C file, I'm going to number include stdio.h. I'm going to declare a variable called thing counter. I'm going to assign a value of 0 to it. And I'm going to put in a function void print thing. All this is going to do is system.out.println. Printf, the value of thing counter is %d new line thing counter, semicolon. That's file1.c. It doesn't really do anything at all. It doesn't do anything at all. I'm going to open up file2.c. In file2.c, I'm going to include stdio.h. I'm going to declare a file scope variable here, extern int thing counter, and I'm not going to assign a value to it. So in file1, I am assigning a value to this thing. In file2, I'm not assigning a value to this thing. I'm going to put a main function here. And I'm going to say printf in main thing counter is, and then %d. I'm going to say thing counter plus plus. I'm going to call print thing. I'm going to forward declare it, but it's in my other file. I'm going to do thing counter plus plus. I'm going to print out the same line again, and I'm going to call print thing again. And at the bottom of this code, I'm going to return exit success. I'm going to go back up to the top here really quickly and include stdlib.h. I'm going to quit this, file 1. I've got file 1 and file 2 here. I'm going to do clang wall-c file1.c-o file1.o. This compiles. I mean, it's not surprising that this compiles. It doesn't do anything. There's not much to it to compile. And now I'm going to do clang wall file2.c. File 2 has my main function, so I can get a program out of this. I'm going to link it with file1.o, and I'm going to call it file2. This also compiles without any warnings. This is what we're expecting to see here. And if I run file2, when I print out in main the value of thing counter is, it prints out 0. This is kind of what I expected. I'm marking this as an extern variable. My linker is going through this, and it's saying that this thing counter and the thing counter that I have in file1.c are literally the same variables. They are literally the same. They have the same address. They exist in both files. They are the same thing. When I call print thing in this file1.c, I'm using the value that's in file1.c. In file2.c, I increment it, and it changes it in both of those places. They are literally the same variable across these two files. Don't do that. As you read C code, this is something that you may see. As you ask ChatGPT questions, this is something that ChatGPT might tell you to do. Don't do it. Please don't do it. Why not? I'm going to leave this as a question for you. Why do you think that sharing data in this way is a bad idea? I'm not asking for feedback right now, but think about it. I'm going to tell you what I think because I said so. It's one thing for us to say this is bad design, but the reason that this is bad design is that my minimal example here is just this is how extern works. But in practice, what we're doing is we're starting to expose implementation details. So if, for example, I have a zone-based memory manager that says, overall, I have this much free space, or overall, this is the head of my list, if I extern that in another file, I'm just accessing private information that I wasn't supposed to access in the first place. I'm exposing implementation details between two things. And this is one of those keywords that we talked about at the beginning of class that we are going to talk about tomorrow. This is causing this measurement of coupling to be high between two different units of code or two different things, two different ideas. If we expose implementation details and we allow someone to rely on the implementation details, then we are tied to those specific implementation details. We'll talk about this tomorrow. So I'm going to go up here to our outcomes. At this point, you should be able to describe concepts of in-application memory management. You should now be able to do both, all of, first fit memory allocation, the runtime stack, and the heap. We will not be doing garbage collection in this offering of the course. Tomorrow, we will describe the benefits of modularity and use simple metrics to specify the degree of independence, such as coupling and cohesion. That's it for today. I hope that you all have a great rest of your day, and I will see you tomorrow. Bye, everyone.